All right, so we're going to talk about multi-stage experiments today, and the first thing that we're going to go back and make mention of is something that you may have seen in the first section, but I didn't bring it up because you weren't specifically asked to do it in any problem set, and that's the idea of a tree diagram. So a tree diagram is a model for a sample space where each outcome is designated by a separate branch. And the easiest way for me to describe that is in terms of the kinds of experiments we were working with last time. So a one-stage experiment, a tree diagram, and you can either draw it opening, left and right, or up and down. It doesn't matter. Your tree can go up, or your tree can grow down, or your tree can grow sideways. Okay. I tend to move sideways just because I have more paper space if I move sideways or down. So you start with a dot, and that represents your starting spot. And then however many different options you have, each represents a branch off of your node. That's called a node. Okay. So for instance, if you were rolling dice, okay, one die, let's say one die, okay, a single die, and it's a plain old standard six-sided die, there would be 6 branches coming off here. One branch would be the number 1, one branch would be the number 2, one branch 3, 4, 5, and 6. Okay? If we were talking about flipping a coin, we'd only have 2 branches because we can only get a head or a tail. So it's a single stage experiment. It's a one-time shot, right? So this is the case where somebody says, I've decided I'm going to have a child, but I'm having one. There will be no second child. We would draw one tree diagram. We have one branch for boy, one branch for girl, and we're done, assuming the husband is first, right? We don't need to control that entirely. Now, a two-stage experiment is my sister-in-law who says, I will have 2 children. Whatever they are, we're done, okay? So with a two-stage experiment, you have one set of branches. I'll draw the branches as though it's the example I just gave my sister-in-law. So the first example is that she would have a boy or a girl when she had baby number 1. And then you take each of these and you draw another node on the end of them. And then no matter what happened after that, her plan anyway was we have baby number 2. But again, each time we have an option or a possibility of having a boy or a girl. So you have 2 sets of branches. One set of branches extending off of another one. And this would be a 2-stage experiment. And can you picture what it would look like if it were a 3-stage experiment? We just add another layer of nodes at the end of where we are, and we draw 2 more sets of branches off of that for child number 1. Okay. All right, multiplication rule for tree diagrams. So for all multi-stage experiments, that's the last example I gave, the probability that an outcome along any half of the diagram, so in other words, if I go back up here with my boy-girl, the probability that I have a boy and then I have a girl after that, the way that I get that probability is that I multiply the probability of having the boy the first time times the probability of having a girl the second time, and when I multiply those 2 probabilities, that is the probability that my path took this branch. Right, that I started here, I had a boy first, and I had a girl second. So let me put some numbers in here so you can see what would happen, all right? So, I have baby. What's the probability of a boy? 1/2. What's the probability of a girl? Better be 1/2, all right? So now, ignore this, right? Let's say I really did have a boy, okay? Had a boy, have baby number 2. What's the probability I have a boy when I have my second child? It's still 1/2. It has no bearing on the first probability. What's the probability of a girl? 1/2. And for exactly the same reason, these are all 1/2s down here as well. And this would be the same tree diagram we would get if we did flipping a coin and its tails. Right? Yeah, it would be the exact same thing except we had each of them T's everywhere instead of B's and G's. Now, the likelihood then that I end up along this branch that I mentioned before is the multiplication of these 2 probabilities. I take 1/2 times 1/2 and I get 1/4. So there is a 1/4 probability that if I randomly choose a family that has 2 kids, okay, randomly choose, I put all the families with 2 kids in the world in a room, okay, and I'll pick one of them out of the hat. That I choose a family that has a boy that's oldest and the girl that's second, I have a 1/4 chance of that happening. Okay, that's equivalent to me saying, if I have I'm starting my family and I really want to have a boy first and a girl second, because I really think every girl needs an older brother. Whatever. My husband thinks that's a good thing. Because he's an older brother to me and younger sister, so this is his idea of being a really good thing. Then I actually would have a 1/4 chance of that actually happening. I have a 1/2 chance of having a boy first, and I have a 1/2 chance of having a girl second, so I have a 1/4 chance of having a boy-girl. Notice I also have a 1/4 chance of having boy-boy, a 1/4 chance of having girl-girl, and a 1/4 chance of having girl-boy. Are you following? Okay. So this is the multiplication rule right here. In red, with a note, I expect to see tree diagrams of all your problems, because this is what your students would do. I know some of you are really good at math, and you do not need to draw a tree diagram to understand how to make this work, and that's cool. I understand that. Same kind of thing when you're working with all of our manipulatives, and you're really good at algebra, and you don't need to draw ponds and whatever to actually make this work. That's not the point, okay? The tree diagrams are what's going to justify your work in this section, okay? So we want to see tree diagrams. Independent events. Independent events are events that have no influence on the outcome of a second event. So these events that are chance, like flipping my coin, right? Or having the children, boys or girls, or rolling my dice, or whatever. There's no effect of one problem on the other. Now, there are not all events are independent events. For example, if I want to know what's the probability that it's going to be sunny tomorrow, well, the weather today affects what the weather likelihood is tomorrow, right? It is not completely independent. My weather today is not independent of my weather tomorrow. Okay, so we don't have this independent property all the time, even though there is some chance in the weather situation. Okay, so most of our events, it's not going to be gray. You're not going to be looking, you're not. It should be pretty obvious. Okay, so if you have a problem with that, we'll talk about when they come. But let's take a look at this one. An executive committee consists of 10 members, 4 women, 6 men. The members are selected at random to attend a meeting in Hawaii. Who is the committee? Okay, just checking. And we want to know what the probability is that all women need to go. Okay, 3 women need to go. Well, this is going to be done with a tree diagram. Okay, so we have 2 possibilities. We select our first candidate that gets to go. And the way that we have set this up is that there's two different things that can happen. I could select candidate number 1 and they are a man, or I could select candidate number 1 and they're a woman. Are you with me? Okay? It's not a 50-50 shot though on this problem, is it? No, because there are more men on this committee that I'm selecting from than there are women. So I'm not going to put 1/2 in here everywhere like I did on the example before. So I select a man or a woman. All right, so what's the likelihood of among those 10 people selecting a class? 6 out of 10. We'll simplify all our fractions at the end. What's the likelihood I select a woman? 4 out of 10. All right. After I've selected and I've reached in and pulled their name out of the hat, I get to select again because I got to pick 3 people that get to go to Hawaii. So I will draw another possibility. Again, man, woman. Okay, now's where you have to be careful with putting in your numbers. We're starting along this path at the top. I selected a man already. How many people's names are still in the basket? 9. How many of them are men? 5, because 1 name has already been pulled. So there is a 5 out of 9 chance on the second draw if I drew a man the first time of drawing another man. How likely is it to draw a woman? 4 out of 9. Say again.
So like if it's on the path of the man, there's really back like a woman to unblock.
Exactly. That was just one possibility and it didn't happen. Yeah, so as you're filling it in, you've got to stick with the path you're on. So now put yourself back at the beginning of the problem and pretend you drew a woman out of the hat. Okay, how many people are still in the hat? 9. How many of them are men? 6. So there's a 6 out of 9 chance along this path that you select a man the second time. How likely you select a woman? 3 out of 9. But that would only be 2 people going to Hawaii, and we need a 3rd person to go as well. Need. Sounds like it's a horrible thing, doesn't it? All right, so here's a man and a woman. man and a woman. Man, woman, one more. Okay. You can only establish this, first of all, regardless of which branch I'm on, how many names are in the house. There's only 8 in the house right now, right? Because 2 people have already been selected, two names are out there. I don't know whose they are, but there's only 8 in there. So all my fractions here are going to have a denominator of 8. Now I can put a pattern on, right? So we're going to go here. If I select man and man, then how many men are left? 4. So it's 4 out of 8. If I select man and man, then how many women are left? Still 4. Now notice this too. These two numbers have to add up to 1, right? 4 out of 8, 4 out of 8, they got to add up to the number 1. So that's always happening here too. They've got to add, the numerators have to add to 8 because there's 8 names. All right, let's do our second path. I select a man and then I select a woman. How many men are left? 5. How many women are left? 3. Okay, now this branch right here is actually the same because now I selected woman and man, right? 1 of each. So how many men are left? 5. And how many women are left? 3. All right, last branch, woman, woman. Woman, woman, how many men are left? All 6 of them. How many women are left? Just 2. Now, the question is, what are the probability that all are women? Well, in essence, this is the path I'm talking about right here. And the multiplication property for the tree diagrams that I talked about on the previous slide says, what do? I multiply those 3 probabilities. You guys know how to multiply fractions. We've already talked about this semester. It's almost like they planned the book that way. All right, so 4 out of 10 times 3 out of 9. Okay, this happened yesterday. I don't know. I'm just going to have to ignore it, I guess. Real? All right. 4 out of 10, 3 out of 9, and 2 out of 8. Oh, and then it went away. You can reduce them and multiply. You can multiply them and reduce. It doesn't really matter. You're going to get the same value either way. I guess I probably would be tempted to reduce them before I multiply. 4 out of 10 is 2 out of 5. 3 out of 9 is 1/3. And 2 out of 8 is 1/4. And then I happen to notice that this 2 and this 4 can reduce to a 2. So I end up with all 1s on top. 5 times 3 is times 2 is 30. So there is a 1 out of 30 chance that 3 of the women get to go. It's not real likely, right? I mean, but it's really not all that likely that all men get to go either. We multiply from that half that all men get to go. That's not very likely either. Most likely is I'm going to have some of both, right? It's one of each. All right, so that's an example. A box contains 5 slips of paper. Numbered 4, 6, 7, or 9. The first player reaches into the box and draws 2 slips and adds them up. If the sum is even, they win. If it's odd, they lose. I don't know about you, but this sounds like a carnival game, right? The kind where they say, give me $5 and if you win 50. Whoa. Sounds like a good deal. You have to be careful because there's always a catch where they wouldn't be playing the game with you, right? All right, so let's figure out what my choices are. So I can write it in a tree diagram. That would be fine here. I'm going to write it sort of condensed, though, and I'm just going to write out a list. So one option is that I pull out a 4. And if I pull out a 4, and it really doesn't even matter what order, because addition is commutative, right? So it doesn't matter if I pull out a 4 and a 6 or a 6 and a 4, I add them together, I get the same thing. So one option is that I get a 4 and a 6. One option is I get a 4 and a 7. Or I can get a 4 and an 8, or a 4 and a 9. And those are the only things that can happen if I pull a 4. Agree? Now, notice it says you reach in the box and draw 2 slips. It would be different. It says you reach in the box, you draw 1 slip, you put the slip back in. You reach and you draw can get a 4. So now I say, okay, now let's pretend I didn't get a 4 at all. Let's say I started out with a 6. Well, I do not need to list 6, 4. Do you agree? I already listed 4, 6. I don't need to list 6, 4. But I do have an option of getting 6 and 7, or 6 and 8, or 6 and 9. And those are now all my options that include the number on 6. So now I say, okay, I'm going to draw 4 or 6, and maybe now I draw a 7. And I can draw a 7 and an 8, or a 7 and a 9. And that's all my options for 7s. And now my last option I don't have listed yet is 8, 9, right? Okay. But the kicker is not what I draw. The kicker is what the sum is after I draw them. So I need to figure out what the sum is for each of these. Okay, so what is 4 plus 6? 4 plus 7? 4 plus 8? 4 plus 9? 6 plus 7? 6 plus 8? 6 plus 9? 7 plus 8? 7 plus 9? And 8 plus 9. Okay, so we're going to go back now and we're going to circle all the people who win. So they are all the number selections that would win. So who wins? When do you win? Even. So this one's even. This one's even. That one's even. And that one's even. Okay, so how many of them were even? 4 out of 10. So you have 4 out of 10, which is a 2/5 chance that you win. I think I already did for 8. I think I wrote it in there right there. So what is the probability that they win? So the probability that they win is the probability of getting an even, which above we said was 2/5, right? Let's change the problem now. Do that because I'm excited to. This is what happens, right? So let's say you win now. You say, okay, great, you won, and I gave you your $50 now. How about you bet that $50 that you just got, and we'll change the game. You're thinking, ooh, I'm on a winning streak. So let's change the game and see what happens. All right, so here's the game now. The game's the same, draw 2 numbers, except what do? We multiply them. Okay, so same numbers as before. So let me see what my numbers were. I had 4, 5, 4, 6, 4, 6. Oh, I didn't have 5. 4, 6, started 4, 6.
Yeah.
Okay, sorry about that. Thank you. All right, so 4 times 6, I have 4 times 7, 4 times 8, and 4 times 9. And then I had 6, right? 6 times 7, 6 times 8, and 6 times 9. I had 7 times 8, and 7 times 9, and 8 times 9. If you want, you can really multiply these out. But I contend you probably don't need to. You can probably look at these and tell me which ones are even. All of the first ones are even. Why do I know that every single one in this list 4 times whatever's even? Because 4 is even. So these are all even. 6 times whatever, that's all even. How about my 7s? 7 times 8 is even. So far I've got these. And 8 times 9 is also even, right? So if we just change the game from addition to multiplication, how likely are you to win? 9 out of 10 times. So probably the con would have gone something like, I lost my money, you kept my $5. Let's play the game again, and I'll change the rules. When I change my rules, I say, okay, let's multiply whatever even I win. And the person who's working with Arnold says, sure, why not? And play the game that works. We're much more likely to win this direction. So it just goes to show you that there are reasons why game rules are set why they are, because of the chances of winning being different. Now, we're going to change gears a little bit and take a diagram instead. This is a diagram of a spinner. So we play lots of board games that have spinners, and this is an example of a couple different kinds of spinners. So suppose the experiment consists of spinning X and spinning Y as follows. Okay, so this is spinner X. Sorry, it's not labeled. This is spinner Y. Find the following, the sample space for the experiment. So the sample space means listing out all the things that could happen. So one option is that you spin spinner 1 and you get a 1. We're going to kind of list it in ordered pair. Not that we have to list it this way, but it works really well here. And after I spin spinner X, I spin spinner Y, and what else could I then be drawing or spinning? A 1. So I could get 1, 1. But I could have also spun spinner 1 and spinner X rather and gotten a 1, and spin spinner Y and gotten a 2. Or I could have done spinner X and got a 1 and spinner Y and got a 3. But those are just all the ways that I got a 1 on the first spinner. But maybe I didn't. Maybe I got a 2 on the first spinner. So I could have gotten a 2 and then a 1, or a 2 and then a, well, how about a 2 first? 2 and then a 2, and then a 2 and then a 3. Just to make sure I capture them all. So this is a sample space. It's a list of outcomes. All the possible things that could happen. Okay? It's not the only way to write this, but it's a way that works pretty well as well. Is that good? Understand? Okay. Now we're going to do some probabilities based on this. What is the probability of spinning 2 even numbers? So take a look back at your sample space. 1 out of 6. There's only one of these that has 2 even numbers, right? One option has 2 evens out of a total of 6 options. So we have a 1 out of 6 chance of that happening. Next it says spinning at least 1, 2. 4 out of 6, right? There's 4 of these different options down here that have at least 1, 2 in them. So we have 4 out of 6, which we would reduce to what? 2/3. How about spinning exactly 1, 2? Right, 3 out of 6, right? Because we would exclude this option here that's 2, 2, because that has more than 1, 2. The other 3 had exactly 1, 2. So this would be 3 out of 6, which Sarah told us reduces to 1/2, which is correct. Okay, you ready to take a look at some stains? The longer I've been a mom to avoid more convinced I am that these numbers can't be right. I came up, but it's got to be higher than that. When I purchased a new shirt for my son, there's a probability of 0.15 stains in the first 2 years. Closer to 0.5. We're going to pretend. If the shirt's stained, there's a probability of 0.2 that I will not be able to adequately eliminate it. That is, there will still be some sort of remnant of color in there. It's not able to get out. What is the probability that my son's new shirt will be permanently stained after the first time he wears it? And the answer is it depends if the shirt's white, right? Well, it does, but we're taking a look at this. So, tree diagram, right? So what I told you earlier on is that we are going to do tree diagrams for most of what's happening here. And this one works really well to do as tree diagram. So what are the 2 options to start with? What happens when my son wears a new shirt? He either stains it or he doesn't. So we've got a stain or no stain. What's the chance he stains it? 0.15. So what's the chance he doesn't? 0.85. Remember, these have to add up to the number 1. So 15% chance he stains it, 85% chance he doesn't. Now, if there's no stain, I don't have to scrub it, right? I just throw it in the washing machine. So this idea of the branches having to extend from both of these, don't on this one. This branch at the bottom where there's no stain is finished. 85% of the time the clothes go in the wash. However, the other 15% up here has 2 options that can happen. It's either stained permanently. It's a permanent stain. Oh, I can't spell it. Or it comes out. Some description of that. It doesn't have to be those exact terms, but you get the idea, right? Those are the 2 things that can happen. So what's the chance that it's permanently stained? after I scrub it. Point 2. What's the chance that I'm able to get it out? 0.8. Okay, so is everybody good with the diagram? Now the question said, what's the probability it will be permanently stained after the first UV wears it? So this is one of my branches. It's the branch along the top, right? This is the question that I'm being asked. The question I'm being asked is, what's the chance that there's a permanent stain when it wears it the first time? So what would I do to find out this probability? 0.15 times 0.2. And if I multiply them, what do I get? 0.03.
Okay, where'd you get the 0.2 or 0.8? Okay, that one. All right.
Yeah. And then the 0.8 came from one minus that.
Okay.
Any other questions? It's just a 3% chance. How to make the numbers come up. Yes. No, I don't. You're going to leave probabilities as probabilities. Yes, so you're just going to leave it as 0.03. Yeah. I mean, they do have a percent form, obviously, but you're not expected to remember anything in this chapter. Unless I guess if the question is specifically asked you, I don't think that it does make you do something. All right, let's see what we have next. Joe says that if a family has 2 children, then the only probability are 2 boys, 2 girls, and 1 of each. This is kind of like our basketball example. Because there are only 3 possibilities, then the chance of having 2 boys is 1/3. Is this correct? Excellent. I already drew this tree diagram. Let me draw it again, okay? So we have a tree diagram. It's boy, girl, 2 kids. So we have a 2-stage tree diagram. You guys remember that, okay? And all the probabilities in this entire diagram are what? 1/2, right? And we're all 1/2. Are there really only 3 possibilities? No, there's only 4 possibilities, right? There's a possibility that we have boy, which he acknowledged. There's a possibility we have a boy and then a girl. There's a possibility we have a girl and then a boy, or a girl and then a girl. There's 2 different ways we could end up with a boy and a girl, and that's what he's overlooking in his simplified analysis of the possibilities here, right? And each one of these, as we talked about before, have a probability of what? They're all a probability of 1/4. Because we would multiply along every branch, and every time we multiply, it's going to have to and so forth down the branches. All right, so here's my diagram, and the question is Joe correct? And the answer is no. Why not? Okay. So there are really 4 possibilities. And we can say what they are, right? Boy, boy, girl, girl, boy, girl. And each has a probability of, I got 1/4. That's what I heard before. So the probability of having 2 boys is what? Right. So 1/4 probability, not a 1/2 probability. Right. Now we have one last example. This is an example from my team.
And if it's low enough, then you don't. And if it's low enough and you don't, then your children won't, except for a genetic abnormality or something like that, which those things happen too, but it doesn't, happen frequently. So if a parent has Huntington's disease like my father does, what it means is that every one of their children has a 50-50 chance of having it. And I have two siblings, myself and my brother and my sister. And my parents had known about this for quite some time before they shared the information with us. So I had been married for almost 3 years when my parents decided to tell us that, hey, you might have this disease. And my sister had been married for almost 1 year. And my brother was seriously dating the woman that he also had married. And so, as you can imagine, this was actually quite a blow to find this out because we saw my grandmother suffer in this disease. What Huntington's does is it actually affects your central nervous system, so it stops your processing time. So the things that I remember from my grandma is I remember going to the golden corral with soft serve ice cream, you have it over your GC2. And the time it took her brain to tell her hand to stop the ice cream went everywhere. You lose the ability to balance. My father is very unbalanced. He's scared. So when the daylight's out, he's walking up and down stairs and sure as he's on his head. You lose the ability to process things correctly. There's some discrepancy about whether or not it actually affects your mind, which I think is probably the worst because if it doesn't affect your mind, it means you're fully aware of things you can't do anymore, and that's hard. My grandmother got to a point where she was fed fast and she couldn't swallow. And so she was being force-fed and things like that. It's terrible, absolutely terrible. So at the point when my parents actually found out that, or told us when we found out that we had this in our family, my husband and I, like I said, we were very decision that if I had this disease, we would not be having children and we would adopt. That's what we decided. This is not a popular decision in our family. They did not like that plan at all. They really weren't even sure they wanted us to go get tested. It's not a simple blood test. You have to go through psychological evaluation and all this stuff to be tested. So let me draw you the tree diagram first for what happens. So I have two siblings, which means that I'm sibling number one. I'm the oldest. So there's two different things that can happen when my parents have me. There's the possibility at sibling number one, me, that I have this, and then there's the possibility that I don't. These are the two things. And what's the likelihood that I have it based on the information I told you? 1/2. You can do 1/2, or you can do 0.5s, whatever you like, fractions or decimals. But then we have child number 2. That's actually my sister. So we have child number 2, my sister. This is a completely independent event. There is absolutely no bearing of whether I have the disease and whether my sister does. Okay? Just like there's no bearing on whether or not she's a boy or girl. She either has the disease or she doesn't. So I'm writing have and don't because I already started that way. And each one of those probabilities is 1/2, 0.5s. And then we have child number 3. That's my brother. And again, he either has it or he doesn't. So we either have the disease or we don't. And all of those probabilities are 0.5, 1/2. So we were actually living in Kansas when my parents told us about this. They were in town for Thanksgiving. And literally, when we were done having this conversation, my husband and I were alone there. This is what I was doing in my head. I didn't create a tree diagram, but I did the mathematics that the tree diagram does. And I thought, oh my word. Take a look at question A. This is what I was thinking about. What is the probability that at least one of us has this disease? Not all of us escaped. Well, the easiest way, let me tell you 2 ways to do this. One way to do this is to take all of these branches that have the word have in them and add them all together. So I would add up branch 1
I would add up branch 2 and 3 and 4 and 5 and 6 and 7. I can do that. It's fine. But mathematically, it'd be a lot easier to do the other option. And that is this idea that we encountered last time, is that the probability of the complement. This is 1 minus the probability that we all don't have it. Let me say it that way. Well, there's only one branch, along one branch that we all don't have it. And it's this bottom branch down here. Okay, I'm not trying to mark it up because I want to keep these diagram for a minute. If I take that branch down there, they all have what on them? 5s, right? So this is 0.5 times 0.5 times 0.5. If you multiply that, that's 0.125. That's 1 minus 0.125. It's 0.875. There's an 87.5% chance of that one of my siblings or I is really, really scary. And that is the decision that we made. We made the decision that if I have this, we're not having kids. If you turn the next page, what you'll find out is that in 2003, I went and I did all the psychological evaluation, and I did the blood work, and I did everything. I do not have Huntington's disease. It's not something you can develop later. It's not one of those, as you get older, something might change. It's a genetic issue, and every bit as much as I'm a woman. You can't change that, right? Not really. That's who I am. It's part of my genetic code. The same thing with Huntington's. I don't have it, which is the reason we have my daughter. Otherwise, we wouldn't. We didn't need to make that decision. We would not be having children. So we have my daughter. But I will tell you also that God does amazing things. Because the reason I have my son is because of this too. Because we started thinking, all right, so many parents, if we don't have kids, if we don't biologically have children, what are we going to do? What then? What's next? And I'll tell you what, the more we thought about it, the more we prayed about it, and the more we just processed this information, the more we felt like that regardless of how this test came back, we were supposed to adopt. So, because of Huntington's, I have my son. And because I don't have Huntington's, I have my daughter. Which I just think is really cool. And it's just amazing how God uses circumstances in our lives to bring about His will in our lives too. So what I want to do next is to show you what happens with this tree diagram, okay? So this question says, in 2003 I was tested, I don't have the disease. What then is the probability that at least one of my siblings does, okay? So if you take a look back at this tree diagram we created before, what we just did is we eliminated me. And we eliminated the possibilities up here. Because I don't have it. We're down on the bottom branch now. The diagram right here is the diagram that we need to work with for the last problem. Because that diagram right there tells me information about what now? What about my sister? What about my brother? So I have a 2-branch tree diagram. We either have it or we don't. We have it or we don't. And they're all 0.5s, right? All right. So what happens when I multiply each one of these branches together? We've already seen the diagram. What do I get? I get 1/4 on all of them, don't I? So either 1/4 or 0.25. I've started working in decimals, so I'm going to keep my decimals, but fractions are fabulous too. So they're all 0.25s. All right, so we're back to the same kind of question that I had before then. What is the probability that at least one of my siblings does have this? Well, as we did before, this is 1 minus the probability that they all, or both in this case, don't. Well, what is the probability that they both do not have Huntington's? 0.25? Right? It's this branch right down here. So there is still a 0.75 chance hanging out there that one of my siblings has Nathan's disease. And just to make things more interesting, they all have kids. My brother has 2, my siblings about to have a second, my sister has 3. So if one of them has it, then their children are pretty shy of having this disease as well. With that, they have not been tested. My sister was going to be tested before she had her oldest son, who's about to turn 9. It's kind of tricky because if my sister were to decide to be tested now, and she had it, she actually had it, then she can't get her children tested. There's genetic, I guess it's law, I don't really know, but you have to be 18 to be tested for a genetic disease unless you're pregnant. You're not a person being pregnant, but like for instance, if my sister had made the decision to be tested when she was pregnant with one of her children, she could have had the baby tested before it was born. Obviously, we all understand the incident that you might want to choose an abortion, which was never an intention she had, so she would never have made that choice. But that is an option along those lines. It's using the genetic testing among other things. So she doesn't want to be tested because she's scared that if it comes back out, then she's got the kids to worry about after that. In perspective to her, my brother decided he would flat out not be tested because it wasn't going to change his decision. He wanted to have children. He wanted to have children biologically, and so it wasn't going to make one bit of difference for him. He wasn't going to make a decision like I made. I was going to make if I had it, so he just wanted to be tested. I do think that if there were ever substantial progress made towards a cure or a delaying of onset of the disease, the onset of the disease is related to the onset of the disease for your parent, plus or minus a standard deviation of 18 years. How to take the statistics, that doesn't mean a lot to you, but that means that there's a 70% chance that it could happen as early as 18 years before it happened to your parents, or up to 18 years after it happened to your parents. I don't know about you, but that's a substantial bit of difference. So my father and my grandmother both had onset of the disease